Okay, as a recap, we are in fact going back to the quadratic formula, and that is a graph that has a specific parabolic shape. Right? In other words, it's sort of like a bell, upwards bell, or it could be a downwards bell, like whatever you want to call it, like a valley or a mountain, whatever. The reason why we talk about a parabola x squared, it's the next easiest type of graph after the straight line. Think about it. Before, when you were doing in grade 9 and a little bit of grade 10, we were talking about mx plus b, and the exponent is a 1. The next hardest one, the next easiest one, whichever one you want to call it, is x to the power of 2. And that creates a funky shape. Why are we looking at different types of equations and trying to graph it? Well, the whole point of math. What is the whole point of math? We have to actually talk about that a little bit. Why do you think math is done in the first place? And it's not to make it painful for you. It's not to make your life hard. If everyone hates math so much, why is it even done? Going once? No? Shot in the dark? Ultimately, it does a really good job of explaining things and why things happen out there. So it's a phrase that I use, and a lot of my grade 12s understand now. I say, if there is a need for it out there, it must be possible in a math class. That's why we learn math. I'll say it one more time. If there's a need, if there is a desire, or if there is some kind of necessity, in the real world, whether it's something as simple as conveyor belts in a factory, all the way to rocket science, to designing your phones, to the metaverse now, right, with Facebook. If there's a need for it, it needs to be possible using numbers in a math class. Math can actually help explain anything and everything with just numbers. And so we're learning about functions. Why? It's the easiest form of technology. When X is something, Y is something. When you have a cause, you have an effect. I'm not going to bore you. I'll just continue on with this. So it is important for us to see if X is something, what happens to the Y? And then from there, what does it look like and how we can use that to our advantage. So we're looking at the basics of the basics. That's why it might be boring to some of you. Anyways, I'm going to plot this out. I'm going to draw it with you. We're going to talk a little bit about some key features. All right. And then you don't even have to look at this. I'm just going to quickly remind you of what happens, but we will look more into it on Monday when you have a fresh brain. All right, here we go. Let's start with 0. 0, when X is a 0, 0 squared, what is Y? 0 squared, it's a big 0. When X is a 1, 1 squared, 1. When X is a 2, 2 squared, 4. When X is a 3, 3 squared, 9. When X is a -1, -1 times -1 is +1, remember. -2 times -2, a +4, and a -3 times -3 is a +9. So let's clarify. It means that's 1 point. When my X is a -2, my Y is a 4. When my X is a -1, my Y is a 1. When my X is a 0, my Y is a 0. When X is a 1, Y is a 1, so on and so forth. Done. Let's plot it. Yep. It is because you are not actually telling the computer the negative is part of the base. So if you do, for example, let me use this bottom page. If you just plug into the calculator of -3 squared, the computer will think you're only applying the square to the 3 and that the negative is multiplied after. You need to specify that the calculator, to the calculator, that the -3 is a part of the base. You need brackets. If you don't, the computer is too smart for its own good. If you want, if the base is a negative, yes. Yes. No. You will see that the computer will say, oh, this is a -3 multiplied by itself. Well, then that's going to be a +9. Whereas here it says, oh, a 3 is multiplying by itself. Then it must be a 9 and the negative comes down. Negative just is multiplied after. I'll say it one more time. If you don't put a bracket, the exponent only applies to the 3. This is what the computer thinks. It thinks it's only 3 squared, and then a -1 is multiplied after. You have to be careful. So even this, you got to be careful. That's why I sort of placed the bracket in there to show you what the x actually is. Please take this time to draw your graph. It doesn't have to be nice and clean, but do your best. Practice makes perfect after all. So 0, 0. Graph is really big, so I'm actually going to do every 2 boxes is going to be 1. I'm going to do this. And every 2 boxes, 2 boxes, 2 boxes, every 2, 2, 3, 4, 5, 6, 7, 8, 9 is as high as I need to go. 1.11, 2, 4, and 3, 9. -1, 1, -2, 4, -3, 9. And now while you're doing this, you might have seen on the internet or any other websites or some kind of movie where they use math and it is all this crazy like graphical stuff like that, right? It is absolutely possible to create those graphics using equations, but those equations are so complicated. If you saw it once, you'd probably be really turned off. You need to be able to handle crawling before walking and walking before running. Okay, so consider this. If I set this up and I connect the dots, and if I have the patience to try plugging in 0.5, patience to plug in 1.5, patience to plug in 2.5, you would see that this actually creates a nice curvature that looks like a bell or a valley in this case. Yes.
Would you put the arrows at the end? Because we have ordered pairs, but we did assume that would go.
Yes. So these chart values are just sort of suggested numbers. But remember, x will belong to real numbers. So anything goes, it'll go on forever and ever and ever. Okay. So with that, there's a couple of things we can do to describe this shape. Let's quickly. Direction of opening. You have 2 choices. Is it opening upwards or opening downwards? A couple of people. Kaylee, I think I'm gonna pick on people per row. Huh? Yeah. Right? The opening, like the mouth, is opening up. So its direction of opening is up. Please forgive the typo. Direction is up. There's a D right there. Okay. Pop quiz. When would it ever be downwards? Charlie? Yeah, there's some kind of minus on the equation, absolutely. And we'll see that next on Monday. Okay, so there is a way to change this. Vertex coordinate. In the math lingo, the term vertex is actually corner. So for example, a square or a rectangle has 4 vertices, 4 vertexes, okay? A pentagon has 5 corners or 5 vertices. In a parabola, it may not be pointy, but we do call it a point, a corner, a vertex. And that would be correct. Does it always have to be 0, 0? Right? I think the obvious answer is no, because if I were to somehow, let's say, I flipped it upside down and I moved it around somewhere, what if I had a parabola like that? Clearly, the corner is not 0, 0. So be aware. We're going to learn more about this on Monday. Axis of symmetry. What's nice about the parabola is that if you know the vertex, you essentially know half of the graph because there's an imaginary mirror right where the vertex is, no matter where. Even here, there is an imaginary mirror right where the vertex is. And we call it an axis, like a line of symmetry. So I'm going to use a little arrow to say this is my axis of symmetry. And how do I communicate to someone what that line is? You give them a short equation. Anyone remember how to describe a vertical line? I'll give you a hint. It's dealing with x. The equation for the axis of symmetry is x equals 0. Let me try to convince you. Let's see. Next row. Leon, if I had a point here, what's my x value? Sorry, I'll start here. What's the point here? 0, x and y. What's my point here? 0, 0. Sage, what's this point? What's my x though? 0, 1. Zach, what's this point? 0, 2. Nessica, what's this point? 0, 3. And Jen, what's this point? Yeah. What's common between every single point? Every single point. Carter? 0 comes first. X is always 0. So this line, I don't care what my y value is, x has always been 0. That's why the equation is x equals 0. Y could be anything. But as a mathematician, and I'm lazy, why would I even write that? Yes, Alex? Yeah, absolutely. Go for it. So I don't have to write this. I just say x equals 0 and y equals anything is assumed. So that's why it's my equation y equals 0. And if this was, let's say, a positive 1 on my imaginary parabola here, it's the same thing. My axis of symmetry, the equation would be x equals 1. Domain. I'm hoping that everyone is very comfortable after the quiz. If this continues on forever, in other words, these numbers continue on forever up and down, what's my domain, Charlie? Yes, x belongs to any real number. Challenge, what's my range? Mm-hmm. Such that, yeah. Perfect. 0 and y. Amazing. That's it. Why am I going through this? Why am I going through this? Unfortunately for you, the easiest way to get through this part of the chapter, in terms of, in other words, The easiest way for you to quickly draw a graph so that you know exactly what the heck we're talking about is if you memorize these points, because we're going to start manipulating these numbers. But there's a cheat. 1 times 1 is 1. 2 times 2 is 4. That's all you need. If you can do that, you've already memorized it. Take a look. 0 times 0 is 0. 1 times 1 is 1, and 2 times 2 is 4. If you can memorize these points, 0, 1, 2 becomes 0, 1, 4, right? If you can do that, you can create this part of the function and then just draw like dotted lines to go upwards, okay? That's going to be your bread and butter for 1.5, 1.6, the rest of this year, really, right? Just give you a heads up. From here, if you can turn the page, we are going to move on and talk about A, H, and K. This year, there will be 3 possible numbers associated with the x squared. They are labeled as A, H, and K. A will be found in front of the x. H will be found subtracting to the x. And K will be found adding at the end. Each of those numbers does something different to the graph in manipulating the shape. So we're going to look at all of that on Monday. You don't have to worry about drawing this, okay? We will get more of this done on Monday. All I'm going to do is try to refresh your memory. And if you haven't done this before, well, you're learning it for the first time. Yes, yes. This is what's happening to the, yes, yes. This is what happens with A, with H, and with K. Just write this down for reference, and we will do this in detail on Monday. What happens when you multiply? The proper wording is the graph will vertically stretch by a factor of whatever that number A is. So anytime there's a number here, you're going to actually see it stretching thinner. And of course, if the A is a decimal or a small, small, small number, you're going to see it shrink. You're going to see it smush. Okay. So the graph will vertically stretch by a factor of A. And would you please put a bracket under stretch and say or compress? Because if you can stretch something, you can definitely smush something. Next, if you take a look here, there is a subtraction of H. It looks like a subtraction. So what happens if you subtract a number here, or what happens when you add a number here? I'm going to do a something slash something. So pay attention. The graph, if there's a number inside the bracket that's subtracting from the x or adding, this will happen. If it's x plus h, it will shift horizontally to the left or right. And by that, it means when I'm adding. So if it's x plus h squared, it actually moves left. Slash, if it's x minus h squared, the graph will actually move right. Okay, let me try to. If the number looks like it's adding, it actually moves left. if the number looks like it's subtracting, it actually moves right, which seems counterintuitive. So it moves left or right by h units. And this time it's a little easier. What happens when there's adding? The graph will shift vertically up or down by k units. Okay, so it would be up would be x squared plus k. Down would be x squared minus k. I don't like that bracket. I'm going to erase it. Okay, once again. There. That's it for today. I want you to keep this in your notes for reference. We're going to go more in detail and see it in action with lots of examples on Monday. But I'm going to save that for Monday because you've had a long day today. Any questions? All right, I'll stop right here.